After lunch is always a tough gig, but I get to talk about three of my favorite things, simulation, energy, and high-performance computing, and I hope I'll keep you entertained, if not just awake. Let me start first by noting that numerical descriptions of the physical world have been around for, well, since Newton, if not before, but they are all necessarily approximate. We have high confidence, and many people who are not in physics don't understand just how high our confidence is in the fundamental description of everyday phenomena: atoms, electrons, photons. Quantum electrodynamics, which underlies all of that, it's tested to a precision of 10 to the minus 12. So that's extraordinarily precise. We have extraordinary confidence in the theory. The problem is that the systems of practical interest are just too complex. If you take a cubic centimeter of ordinary matter, it's got 10 to the 23rd atoms in it, with 10 to the minus 7 centimeter spacing between them, so that there are 10 to the 7th atoms in each dimension that you're looking at. Those atoms vibrate with periods of 10 to the minus 15 seconds, while the characteristic time for sound to cross that 1 centimeter is 10 to the minus 6 seconds. So it takes a billion time steps if you're going to describe every atom to describe the physical phenomena that we're usually interested in. Similarly, if you take radiation at, say, 6,000 Kelvin, a cubic centimeter of that has got 10 to the 13th photons in it. There are just too many things to track directly. And consequently, direct simulation is really tough, and we need to learn how to reduce the degrees of freedom. We have done that largely in the paradigm of partial differential equations and their numerical solution. We define fields in space and time, the density, the velocity, and so on, that are constructed by averaging over many atoms. We then write down differential equations for those fields that conserve energy, mass, momentum, and so on. And then we lay a grid on those differential equations, turning them into difference equations that can be solved, evolved in time numerically, step by step, in order to let us understand what the system is doing. It's pretty clear that higher resolution can improve fidelity. If I go from some discretization spacing to something half as big, I can obviously get a better description of the system. Unfortunately, it's not as simple as that. First of all, the computational work that you have to do scales as the inverse fourth power of the spacing. 3 powers from each of the spatial dimensions, x, y, and z, and then 1 power because as you make the spacing smaller, you have to take smaller time steps. You can't let the system move too much from one time step to the other. Unfortunately, what that means is that to have the spacing to go from delta x to delta x over 2 requires almost 2 orders of magnitude in compute power. And so the exponential growth that John mentioned this morning, and I'll show in a bit more detail in a moment, quickly gets eaten up as you try to do a better and better description of the system. The second point is the algorithms, the ways in which you turn the differential equations into difference equations. People have known for a long time that they are not necessarily stable, so you have to worry about that as the spacing gets smaller. You have to worry about whether you have converged in the spacing so that your physical answers are independent of the spacing, and of course the accuracy with which you're trying to do things. Beyond the mathematics, and all of that is mathematics, there is physics. There are so-called subgrid scale assumptions. Even with gridding up the problem, there are still physical phenomena that you have to make models and assumptions about. Reduced models. For example, if you take a modern climate model, the resolution in the atmosphere is about 1 degree at best. So that's 60 miles. On the other hand, we know that there are phenomena like thunderheads, hailstorms, and so on, that happen on scales of 1 mile or less. And so when you build the model, you're going to have to make assumptions, subgrid scale models about what all that microphysics is in order to be able to solve the bigger problem. There are microscopic data that you need to know, whether it's the radiative properties of atoms or the equation of state of the material within a grid cell. You also need to build that into whatever your description is. Then we have problems with spatial non-locality. There are some phenomena, particularly neutrons, neutrinos in supernova, photons, that can go from one grid cell all the way over 10 or 12 grid cells away. And if you're trying to put this problem onto a computer, that non-locality in gridding can make trouble for you. And then finally, there are always parameters, physical parameters, numerical parameters. Being able to explore the sensitivity of the modeling to those parameters, to quantify your uncertainty, whether it's due to the initial conditions or to the physical parameters, is very important. And that means you don't only want to do one run of a particular simulation, but you want to do 1,000 of them to get a feeling for the variation. And so more computing power, which we'll talk about in a bit, certainly helps in that dimension as well. Also, problems just listing the kind of things that we need to deal with. Variable resolution. Sometimes in a problem there's one bit of space or time where there's a lot of action going on and you want a very fine gridding, and there are other parts of the problem where you're content with a more coarse gridding. Being able to manage that disparity is also important. Visualization. As we had some discussions this morning, before we started today, I was involved. These codes that describe physical systems are great data generators. And I started computing, you could do one dimension, it was fine, you could look at the numbers on a piece of paper. Even in 2 dimensions, you could get pretty good at it. But in 3 dimensions, there's just no way that you can absorb all of that by staring at numbers. You need to look at the thing through your eyes, the fastest data channel into the brain, and how do we do that is a problem. And then validation, especially in 3-dimensional calculations. You can compute in great detail what's going on inside a complicated system. How do I do the experiments that let me see inside in order to see whether the code is describing the phenomena appropriately? And what variables do I look at? When I can produce thousands of variables describing the system, which are the most important ones to validate that I'm getting them correctly? These are all problems I think are at the forefront of what we're trying to do in high-performance simulation. All of that has driven, first, an evolution of the hardware. And this graph shows the machines at the top of the top 500 rankings every year since 1996. It has a particular Department of Energy focus because, in fact, much of that evolution, over a factor of about 1,000 or more over the last 15 years, has been due to the Department of Energy's concerted efforts in a stockpile stewardship program to replace the underground testing of nuclear weapons with high-performance simulation. However, if you look at this list, and I'll come back to it in a little while, what you realize, given everything I was talking about in the previous slide, that the machine is not enough by itself. Raw flops are not what makes this work. As I like to say sometimes, the machine is just the golf club. The swing also matters, maybe more than the golf club itself. All right? And so we have programs, and here's an example from understanding the internal combustion engine, where you build real systems. You have diagnostics that let you see inside of it. You do laboratory experiments. You do microscopic work on the molecules and the kinetics of the fuel. And then you put it all together into a model that is actually useful for you. And so I and many other people in the business are somewhat skeptical of, well, I've got a really big machine. I'm great. It's all this other stuff that you need to do in order to use it very well. Here's an example just to show you the kinds of phenomena that get explored computationally. These are just jet flames of two different chemicals. You can see that they're in different concentrations in the flame. This is all simulation. You can look at all the rich detail. And the question, of course, is always, is any of that right or not? And if so, you can then build this into your engine models. Okay. Simulation has, in fact, already started to penetrate into industry and into energy systems in particular. This is just a list of some of the bigger companies that have adopted simulation and what they've been able to do with it. Boeing famously for aircraft design, Cummins for bringing engines to production faster, Goodyear tires and so on, all familiar examples. One of the things we are trying to do in the department, which is a great reservoir of simulation expertise as a result of the nuclear weapons work, is to migrate this further out into industry. These are all big companies. How do we get this into small, medium-sized companies as well? Okay, I then want to shift gears a bit and talk a little bit about energy, and I'll try to bring the computing aspect into it in a moment. I would note that we're coming off having spent 8 months doing a study inside the Department of Energy, the so-called Quadrennial Technology Review, which was released a couple weeks ago. You can get it at that website, which tries to answer the question, well, so what does the Department of Energy actually do in energy? For those of you who may know our budgets a bit, we only spend about 15% of our budget in energy technologies itself. The biggest chunk is in nuclear security. The second biggest chunk is in environmental management, cleanup, and the third biggest chunk is in basic science, and after that you get to the energy technologies. Nevertheless, given the prominence and importance of the energy problems we're facing, it seemed like a good idea to try to answer the question, well, exactly what do you do? What should we be doing? And of course, how do we get it done? So you can find some of the answers to that in the PDF that's posted up on that website, but let me take you through some of the thinking. I think the first thing is to clearly understand what problems are you trying to solve. And we came to see that there are really 3 different challenges associated with energy. The first is energy security. This is, in the US, almost entirely about oil, and it's due to the fact that the US is coupled to the world oil market, making oil prices A, volatile, and B, currently pretty high. Associated with that is the fact that most of the world's conventional oil reserves are not accessible to the big independent oil companies, but are rather in the hands of the national oil companies, Saudi Aramco, PDVSA, Petrobras, and so on. So that's one problem. Quite different problem is the issue of US competitiveness. This shows in 2009 the lithium-ion battery manufacturing around the world. You can see that even though this was a technology that was invented and refined in the US, we are currently manufacturing about 1% of the batteries for consumer electronics, the great bulk going on in Japan, China, South Korea. I can tell you the same story about photovoltaics. This shows PV module manufacturing sales around the world. The US is down at a few percent share right now. Great growth in China, other parts of the developing world. Again, you can read about this in the papers these days, of course. And the same is true for other energy technologies, whether it's nuclear, it's wind turbines, it's fuel-efficient automobiles. By and large, the US is not manufacturing the new energy technologies. The third issue is environmental impacts, most famously carbon dioxide and its effects on the climate. But equally important are, for example, water issues. More than, or just about half of the water withdrawals in this country are due to generating electrical power, more than in agriculture. And obviously this has implications for what technologies we might deploy to generate electrical power in the future. Well, dealing with those problems, how you're going to do that, the first thing is to understand the energy system. And I like to talk from this somewhat complicated chart. It's complicated because Livermore did it. That's what we pay the labs for, right? They're like some consultancies in the business world. We're not going there. Which shows various flows, sources of energy on the left, uses of energy on the right, and the bars indicate the magnitude of the various energy flows. Lots to learn from studying this chart, but I want to point out a couple things that are important to understand how we're going to deal with the energy problems. The first thing, of course, is that petroleum feeds transportation almost entirely, and transportation is fed just about exclusively by petroleum. And that means you can more or less draw a line across this graph and separate out the transport sector from everything else. And so it drives me crazy when I hear politicians and even people who should know much better saying we're going to fix the oil problem by building more wind turbines. All right? It's just completely disconnected. There are other things we can talk about, my favorite energy pet peeves. The second is that electrical generation is fed by multiple sources. Coal, most obviously, that big black bar going up, but also natural gas, geothermal, solar, and so on. And then finally, natural gas, you can see, is split about evenly between electrical generation and residential and industrial heating processes. The other thing to learn from this chart is that we're pretty inefficient in using energy. If you look at the so-called rejected energy compared to the total energy that we use in quads or equivalently exajoules, our efficiency is only about, 40%, something like that, at best. We waste a lot of energy. Now, if you know anything about the second law of thermodynamics, you know you have to waste some energy. But if you look at other societies, there's a lot we can do in efficiency. The last thing, somewhat amusingly, is if you take the rejected energy in each of these three boxes, industrial, commercial, and residential, it's exactly 20%, 0.20 of the total energy in the box. And that's not a coincidence. It means that somebody guessed as to what those numbers are. And it highlights, it's true, it's true. It highlights the fact, and now we start to get to some of the data discussion, that in fact we have very poor information about how energy is actually used. And if we're going to do anything about the efficiency problem, we really need to understand that. Okay. Beyond those numbers, there are a couple of facts about the energy system that you really need to understand if we're going to try to change it. For the first part, it's a big and expensive system. It's big in the sense that it moves a gigaton of coal a year, most of a gigaton of oil a year. There are 250 million vehicles on the roads. There are 120 million households and so on. So the numbers are very big. There's also a lot of capital tied up in the energy system. If you add up power plants, transmission lines, refineries, pipelines, automobiles, there's a good fraction of the annual GDP, about $14 trillion, that's tied up in that system. The second thing is that the system is in private hands. Nothing is going to happen unless somebody can make money changing it. All right, that is fundamental, but there are some audiences I talk to for whom that is a revelation. Energy is wonderful. And obviously it's governed by economics, but the government gets to modulate things through the regulations that it puts in place. On the supply side, so the left-hand side of that chart I showed you a few minutes ago, the energy system is run by fewer long-lived facilities that are really expensive. There are 15,000 generating plants in the country, less than 100 refineries. They are expensive. A nuclear power plant costs $8 billion. A coal-fired plant costs about $3 billion. They are long-lived. They last for decades. And what that means is that things change very slowly. Let me show you what happened to, there it is, that one I wanted to show you. This shows the US energy supply since 1850, 1 bar per decade. And you can see at the time of the Civil War, we got most of our energy from wood, and that as the decades went on, the Industrial Revolution, coal became important, the gray bar, oil became important as transportation became possible, gas, the pink bars, nuclear, and then the renewables, that little pink sliver up in the upper right the last couple decades. The lesson to draw from this chart is that things do change. They change in response to technologies, they change in response to regulation, and of course in response to economics. However, it takes decades to change. And if I sometimes show a chart in which you look at the evolution of IT just within 1 decade, and it moves, of course, exponentially faster. And so many people get fooled by the evolutionary pace of biomed or IT, thinking you can do the same thing in energy. And there are some structural reasons why it's really difficult to do that. The other amusing fact about this chart is that the absolute amount of energy that wood supplied in 1850 is the same as the absolute amount of energy that it supplies today. It's just that everything else has grown so much. Another thing to understand is that on the supply side, what you're producing is power, electrons, and fuel, molecules that work in vehicles. And those are commodities. You can't tell the difference between one electron and another. And despite what you might hear about premium gasoline, all fuel molecules are pretty much the same also. These are commodities, which means that the businesses supplying them are working on pretty thin margins. And that means when you go to do a project, you have many levers that you can pull. The way you operate the project, the market conditions, guaranteed supplier arrangements, and so on. Technology is only one lever, and it is often a weaker lever than the others that you have. And so this is a very conservative business technologically. In part, in the power sector, the lights have to work. And so you don't naturally take many chances. On the demand side, things are somewhat different. There are many distributed players, 300 million consumers, as I mentioned. The assets are shorter lived. Appliances last less than power plants do in terms of lifetime. Automobiles turn over every 15 years, roughly. They're not operated on the demand side for profit. Rather, it's for economics, convenience, and personal preference, particularly. And we have paid little attention in the power system to optimizing the system as a whole. You just generally generate the electricity into a dumb load, and there are many opportunities to optimize that particular piece of technology. Well, you look at all of that, and you say, okay, what am I going to do? And in the Quadrennial Technology Review, we thought that you could write down 6 strategies, 3 of them for transportation and 3 of them for the stationary sector, cued to that energy flow diagram that I showed you before, that if you could do each one of these things, you'd get a long way to dealing with our energy problems. And if you don't do them, you're not going to deal with them. It is pretty much that simple, and we've been trying to lay it out for the decision makers like that. Each one of these involves a mix of technology, regulation, and economics. You need to get them all to play together. I think the government has been notoriously bad at making that synergy happen. Nevertheless, there are opportunities for technology here. I'd like to go through them one by one and show you particularly where simulation and computing can play a role. And let me start with the first one, which is to increase vehicle efficiency. I forgot to tell you something before I get to vehicle efficiency. There are 3 ways in which high-performance computing and simulation, I think, play in energy. One, obviously, is optimizing design. If I can simulate I can make the design cycle for whatever it is I'm building, whether it's a vehicle or a power plant, go faster and faster. The third one listed here, optimizing operations, obviously true also, the electrical grid being the prototype of that. But there's one that is unique to energy, and that is facilitating the transition to scale. If you're building a big facility like a power plant or refinery, even if it's a biorefinery, you're going to do some stuff in the lab, you're going to get the bugs right or the catalyst right, and then you're going to go through a series of scale-ups from, let's say, test tube scale to 1 liter scale to 100 liter scale, typically by a factor of 30 to 100 in each stage. That process can take a total of 15 years to go from the laboratory to one full-scale demonstration. If we can model and simulate, you can make that transition, we think, go faster. And so that's something that is, in fact, unique to energy. So let me talk about the vehicle efficiency. I've already talked a little bit about internal combustion engines. Here's a different one having to do with aerodynamics around a truck. There are 300,000 of these Class 8 trucks sold annually using the Jaguar computer. Sorry about that, guys, but I'm sure it would have run even better on Blue Jean or something like that. All right? You can do CFD and understand that if you put some plastic fairings under the truck, you can reduce the drag significantly and get an improvement of 7% in fuel efficiency. It doesn't cost very much to bolt on a couple of pieces of plastic. Trucks last 3 or 4 years, and so one can go ahead and do this and make money doing it. Not a bad thing to do, right? Okay. Electrifying the vehicle fleet is the next thing we need to be doing beyond increasing vehicle efficiency. Why am I saying electricity as opposed to hydrogen or methane that you may have heard about as an alternative fuel? And the answer, I think, largely is because we can progressively electrify the fleet. We can go in steps from an internal combustion engine, which already can be made actually more efficient than we're doing currently, to a hybrid vehicle like the Prius, to a plug-in hybrid vehicle like the Chevy Volt that gets some of its energy from the grid and backup energy, if you like, from a chemical fuel, and then finally all the way perhaps to a battery electric vehicle. The challenges in making this happen are the batteries, the cost and performance. We'd like to drive them down by at least a factor of 2 over the next couple of years. The supply chain to make all this happen, and then the charging infrastructure. Well, if you go to plug-in hybrids with perhaps modest batteries, you don't need much of a charging infrastructure. You do it at home, and with a vehicle like the Volt, let's say a 40-mile electric range, you can already, for many consumers, cut gasoline use by 2/3 because your trips are pretty short and you charge it up at home every night if you've got the facility to do it. So that's why we like electricity. There is computing to do here. This chart gives you a sense of what's involved. We need to deal with things down at the molecular or atomic level, density functional theory, a way of solving the electronic problems around atoms, molecular dynamics, mesoscale descriptions, and then all the way up to the thermal problems of the battery pack itself using finite element modeling. A different kind of scale problem, simulations that can bridge this scale from the atomic all the way up to the macroscopic, is something that we are, in fact, working on. Let me talk about alternative hydrocarbon fuels for a second, biofuels. Even as we increase vehicle efficiency and shift some of the demand to electricity from gasoline, we're still going to need liquid hydrocarbons to run the heavy-duty fleet. For those of you who perhaps might not have thought about it, the gasoline nozzle that you put into your tank pumps about 15 megawatts of energy. And if you think about the electrical cable that you would need to carry 15 megawatts, you can understand that chemical energy is just much more dense and accessible than electrical energy. And consequently, to run big vehicles, you're going to need that chemical energy. Because of greenhouse gas considerations, domestic production, there are biofuels, for example, that we can and should be producing that can satisfy that demand. The basic problem is to take a variety of sources of carbon, whether it's plants or coal, municipal solid waste, natural gas, run it through a variety of chemical processing, whether it is a biological process or a thermochemical process, and produce the stuff you want at the end. So this is large-scale biological or chemical engineering. Many problems associated with that, but one where computing is playing a role is in the protein folding discussion that Matt mentioned before. There is this wonderful protein that comes from a fungus that takes the cellulose, the structural material of the plant, most of what ordinary plants are made of, and just chews its way along this chain of sugars and splits them up and spits out the sugars. We can then take the sugars and feed them to yeast or other microorganisms and turn them into fuel. How this enzyme works and chews its way down the chain, how is it related to the particular sequence of the proteins involved, is a great molecular science problem that's got very real and immediate applications to dealing with one of the energy problems. So we're working on that. Let me move to the stationary sector a little bit. On the stationary side, again, the first thing you do is work on energy demand, buildings and industrial processes. 40% of US energy consumption is in buildings. You can see here it's slightly different for residential than it is for commercial, but basically it's lighting, it's space conditioning, and then a little bit of refrigeration in the commercial sector. And water heating, of course, is important. This can be made much more efficient than it is right now. I'll give you one example. If you go to NREL, the National Renewable Energy Laboratory in Colorado, they have just within the last year opened up a big new administration building, an office building. That building was built for a cost that is no more than the cost of other buildings in that area measured on a square foot basis. Nevertheless, it only uses about 30% of the energy that other buildings use. That's because very careful attention was paid to the design of the building, the instrumentation of the building, and the operation of the building. So that can be done. You just have to understand how to do it. One of the ways of understanding how to do it is to think about buildings as a system. How do I integrate the HVAC, the air conditioning, together with the windows, together with the utilities in the building, and so on? Buildings are, in fact, a system. Clearly, the physical instrumentation to do this is not difficult at all, but we're pretty lousy at predicting the properties of buildings in terms of energy use and also in helping to operate them in real time. So another place where computing and high-performance simulation can play a role. I'll say a couple words about the grid. It's already been mentioned slightly today. The grid is, when you talk about it, a revelation to most people. We've done such a great job of hiding that infrastructure that most people don't think about it at all, except when the lights go out. It is, and this was, I think, wasn't this the engineering achievement of the century from the National Academy of Engineering, right? So 200,000 miles of wires carrying a terawatt of power. Unfortunately, there are over 3,500 utility organizations and 5,000 organizations in total that touch the grid in this country and have a regulatory or operational say over it. And that makes a bit of a problem if you want to change things. What do we need? Reliability. When one lineman in Arizona can take out power to over 1 million people in San Diego for more than a day or so, you know you've got a reliability issue. Right? Efficiency of the grid is really important. Not so much for the energy, the electricity that's lost in the wires. That's only about 6 or 7% on average of the electricity. But the fact that because you can't store electricity in real time very easily. You've got to turn on the generators in order to match the load. And who gets to turn on when, and how do you manage the load relative to the generation? There are great efficiencies that can be captured there if you have the right instrumentation and control of the system. Security, really important as we go through what is basically a data overlay onto the physical system. Renewables. We all would like to integrate more wind and solar into the grid. Those renewables are intermittent. They generate when they want to. Being able to anticipate when they generate, handle that electricity they can produce by turning down other modes of generation on 10-minute timescales is also really important. Power quality is something most people don't think about. It's not written up here. But we rely on 60 cycles. And one of the ways in which that stability is enforced is by having big rotating machinery coupled to the electrical grid. As we go to lighter things like wind turbines or photovoltaics, which of course don't have anything moving but have electrical or electronic frequency control, it gets harder and harder to ensure that stability. So that's another very important control problem to be working on. Challenges, basically, I've said them: active management to balance things, and then, of course, making sure that excursions from the ideal, which can be catastrophic, don't happen. Here's a good example of the state of grid modeling. This shows the power flow between California and Oregon in real time during some event 15 years ago. The real world in terms of power flow in megawatts is shown up on top here, and the model that they were running at the time does that. So understanding all of this, pretty important. People have thought about what you need in order to do the modeling right. I think we're pretty confident that up to 10 teraflops or so can be used in the next 3 to 5 years. It's not being used, in part because, again, it's operational folks who are concerned with this, and they've got things working pretty well, and please don't go in and change it. All right, so learning how to integrate with the operational people is really important. Some people believe that we'll need an exaflop in a decade or so. I'm frankly somewhat skeptical of that in this case, but I put it up there as an example. Finally, clean electricity. We are exploring in the department many ways of producing clean electricity. I want to drill in just a little bit for computation in nuclear energy. Again, the scale of what you need to model and simulate to do a reactor properly is astounding, from the femtoseconds all the way up to years of embrittlement in the reactor vessel, for example. We have started in the last 2 years an activity at Oak Ridge called CASTLE, the Consortium to Simulate Light Water Reactors, which is meant to bring high-performance modeling and simulation to understanding of the materials in a reactor and the fuel bundles in particular. Again, somewhat to my surprise, the industry, the nuclear reactor industry, is quite a bit behind what the state of the art is when you look inside the national laboratories or what we can do. The obligatory pretty picture of the power density inside a core of some reactor. This particular consortium has real power operators who have real reactors running, and they are letting them do instrumentation in order to get validation data for the codes. Let me skip through this because we're running out of time, and I'd like to save some time for exascale and questions. There is a similar simulation initiative going on for carbon capture and storage. So we are trying to bring modeling and simulation to these large facilities in order to let us construct them more efficiently and better. So, all right, back to the hardware, and you can see that we have extrapolated this graph up to exascale, 1,000 petaflops by 2020. That's an ambition that some of us in the government have, and I think is shared by people in the laboratories and the private sector. It is more or less on the trajectory. right now, but there are some real problems, as John mentioned briefly this morning, in getting there. We have put together what we think is a program to make that work. It's R&D on the hardware. Power has already been mentioned. In my mind, reliability is another big issue. If you have an exaflop, you have each core running at about a gigaflop. That means you need of order a billion cores. Whether it's 100 million or a billion, we can argue. But when any one of those glitches, in principle, it can bring down the whole machine unless you have organized your calculation and operating system to allow for robustness. So that's a big problem. Power in the memory has already been mentioned. What technologies we're going to use, still up in the air a bit. How do we co-optimize the hardware, the balance between processors, memory, bandwidth across the nodes, together with the codes, is a major challenge. We've started activities out in the universities. I know people in industry are also thinking about how you do that. Let me just say a word then about money. Congress is listening. The FY12 budget, particularly what came out of the Senate a couple weeks ago, has got $126 million in it for the Department of Energy to get started on this program. Figuring high in people's minds in the political sphere are the competitiveness aspects of it, as well as the bragging rights. It's the first time that the budget explicitly mentions the word exascale, and we're shooting for about a decade in order to get an exascale capability on the floor. And the department has already started up a number of activities in the labs and the universities, discussions with the private sector about how we can move this forward. And with that, thanks for your attention. We got time for a couple questions.
Question about the strategy for transportation. Among the three strategies, you didn't mention anything about infrastructure or maybe moving from one mode of transportation to another.
So let me talk about infrastructure. So the question is, I didn't say anything about infrastructure for transportation or intermodal mode shifting. On the infrastructure, in fact looms very large in our thinking. If you want to go for light-duty vehicles only, not for heavy-duty. Heavy-duty is a separate story because you can pull into a depot or have your own filling stations along a trucking route. But for passenger cars and light trucks, we already have one infrastructure, the gasoline infrastructure. We have something of an electrical infrastructure which can do for a while. If you want to shift to hydrogen or natural gas, you got to put that infrastructure in, and nobody has really told a good story about how that's going to happen. So that's another reason we like electricity. With respect to intermodal transport, great idea, but as you may know, energy responsibilities are spread across the federal government. And when we did this study, we concentrated on DOE things. Hopefully, it is a run-up or a forerunner of a broader study that engages Department of Transportation and other folks that we can talk about intermodal. And then let's go over here.
You mentioned the cost of building a nuclear plant, very significant. Assuming the computer was already there, so we'll remove the computing costs. If you could do all the modeling you want, what would happen to that cost?
I don't know, all right? And the reason I say that, well, two things to say about nuclear costs. Anything that gets deployed in this country, and in fact almost anywhere worldwide, has got to get through the Nuclear Regulatory Commission. Those folks are, in my mind, justifiably conservative in what they certify. Modeling and simulation is a big part of what they do, but my guess is it probably won't go any faster if they had better modeling. With respect to the cost of nuclear, one of the initiatives the department is trying to make happen are the so-called small modular reactors, where we would get licensed and construct reactors that are 1/4 to 1/10 the size of the big ones. And there are many advantages to being able to do that not least of which is standard build, factory build, come down the learning curve, truck them out of the factory on flatbeds or in containers, et cetera, et cetera. Plus the cash flow from the first one helps you construct the second or third on a site. So we're trying to get that going. Somebody here?
Yes, Cheryl Watson, Watson and Walker. I was around in the 60s when photovoltaics really made really changed the thought stream of where energy was coming from. And what happened at that time was that the energy companies bought out the patents and then did nothing with them. And it's only recently that they've been able to get around that. Is that still happening with the corporations? Are they buying up what could be potential options?
So I have not seen evidence of that. I can tell you when I was in BP and was in the middle of all of that in at least one big energy company. Yes, we were buying up companies and intellectual property, but to actually pursue them and to try to make it into a business, particularly biofuels, wind, some of the other big energy companies are doing the same. So I have not personally seen any evidence of that kind of blocking.